Okay, this problem reads that we want to verify the linear speed of an ultracentrifuge is about a half a kilometer per second. So for a centrifuge, an ultracentrifuge, I'll put ultra, has a linear speed of about a half a kilometer per second. So that's part A. If the linear speed on a point of an ultracentrifuge is 0.1 meters from its center and it rotates at 50,000 revolutions per minute. So we have the rotational speed of 50,000 revolutions per minute and the radius of 0.100 meters. All right, we know that the linear speed at that radius is equal to omega, the angular speed, times the radius. But that angular speed has to be in radians per second. So let's turn our rotational speed of 50,000 revolutions per minute to radians per second. We know in 1 minute we have 60 seconds. That's going to get rid of those minutes. And there are 2 pi radians in 1 revolution. So that gives us an angular speed of 5.23 times 10 to the third radians per second. Now I'm going to plug that in to my linear speed. So we have 5.23 times 10 to the third times our radius of 0.100, and we get a linear speed of 524 meters per second, which is about 0.5 kilometers per second. Check, we verified it. All right, so the second part of the question says if the linear speed, having trouble speaking there, of the Earth in its orbit about 30 kilometers per second. So we're going to follow the exact same process for this question that we just did for the ultracentrifuge. We have to know a little bit more information. All right, so the first thing we need to know is what is the radius of the Earth's orbit about the sun? Well, we are going to determine, so the Earth is about 30 kilometers per second. All right, so if this is the sun, and here's the Earth going around the sun, and we're supposed to assume a circular orbit, this radius, we would have to look that up. When we look that up, we find that the radius is equal to 1.49 times 10 to the 11th meters. So we're going to remember that radius. All right, we know that the linear speed, again, is equal to omega times the radius. We'll have the radius. So it's going to equal my omega times 1.49 times 10 to the 11th. So I got to figure out omega. We know that the Earth goes around the sun in 1 year. So the Earth makes 1 rotation in 1 year. But I need my omega in radians per second. So we got to convert 1 rotation in 1 year to radians per second. We know in 1 year we have 365 days. And in 1 day, there are 24 hours. And in 1 hour, there are 3,600 seconds. So finally, so my hours cancel, my days cancel, my years cancel, and I end up with seconds on the bottom, but I still have rotations on the top. We know there are 2 pi radians in 1 rotation. So we end up with omega, which is equal to 1.99 times 10 to the minus 7th radians per second is our omega. So I can plug that in up here. We get 1.99 times 10 to the minus 7th times 1.49 times 10 to the 11th, and we get a velocity of 2.97 times 10 to the 4th meters per second, which is about equal to 30 kilometers per second. Check. All right. So again, recognizing two things that we want to look at that linear velocity. It's related to the angular velocity and the radius. So we have to look up that radius. We also have to remember that that angular velocity needs to be in radians per second. Okay, good job.